Let us see basic performance parameters of a transistor. The first performance parameter of a transistor is base transport factor. So we can see what is a base transport factor. So we assume that the collector current is entirely made up of the holes that is injected from the emitter, which are not lost due to recombination in the base. So for a PNP transistor, we know that the emitter will emit holes, and a few of the holes will recombine at the base, and the remaining holes will reach at the collector, and that contribute the collector current. So we assume that the collector current is entirely made up of that holes only, and that holes coming from the emitter only, and which are not lost due to recombination in the base. So we can see that this current IC is proportional to the whole component of the emitter current IEP. So that's a majority case. For a PNP transistor we are saying. So for a PNP transistor, the collector current is proportional to the holes injected from the emitter. So that we can represent it as IC is proportional to IEP, and that proportionality constant is called as B, and it is known as base transport factor. So B is simply the fraction of injected holes which make it across the base to the collector. So how much holes cross the junction without recombination, that factor is indicated by this B, that is base transport factor. So for an efficient transistor, we would like B to be very near unity. That means our requirement for a good transistor is IC nearly equal to IEP. So for that we need to make this B is unity. So for an efficient transistor, the B should be nearly unity. The emitter current should be due mostly to holes, and most of the injector holes should eventually participate in the collector current. So we are assigning that most of the holes will reach at the collector and they will participate in the collector current. So the proportionality constant, how much holes which make it across the base to the collector, that is indicated by this base transport factor. Second parameter is emitter injection efficiency. So we can see what is emitter injection efficiency. So we said that for a PNP transistor, the emitter is made up of holes. The majority carries at the emitter side as holes. So that holes will diffuse from emitter to base through the forward biased emitter base junction, and that will accelerate it towards the collector junction. So this motion of this holes to this base region through this forward biased emitter base junction will cause an whole component of current, that is represented as IEP. Similarly, due to the forward biased emitter base junction, this electrons from the base side will also diffuse from base to this emitter region. So that current contributors are called electron component, and that is represented as IEN. So at the emitter side we have two components of current, that is IEP and IEN. So for a good transistor, our aim is this emitter current is entirely due to this whole current, and this base current should be negligible. So current due to electrons component should be negligible. So we can see that the total current I, the practical case, the total current I is made up of two components, that is whole component IEP and the electron component IEN, due to electrons injected from base to emitter. So using this we can define this emitter injection efficiency as the ratio of the whole component of current to the total emitter current. So this IEP to IEN plus IEP ratio is called as emitter injection efficiency. So for an efficient transistor, we already said that this base transport factor should be nearly equal to unity, and similarly this gamma also should be equal to unity. That means IEN should be very less, or this IEN plus IEP nearly equal to IEP itself. Then we can make this gamma nearly equal to 1. So we are saying that this most of the, that means if gamma is 1 means the most of the injector holes should eventually participate in the collector current. That means the collector current is made up of the whole component of emitter current only. So in that case only gamma becomes a unity. So for a good transistor, the base transport factor B and the emitter injection efficiency gamma should be nearly equal to 1. So the third parameter is current transfer ratio. We already defined this. The current transfer ratio is represented as alpha, and it is the relation between collector to emitter current. So the what is the ratio of IC to IE? That is represented as alpha. So that is called current transfer ratio. So IC, we already said it is BIEP, and we can see IE is consist of two components, IEN plus IEP. So IC by IEP we can represent as BIEP divided by IEN plus IEP. In that IEP by IEN plus IEP is gamma. So you will get IC by IE is B gamma. That ratio is called as alpha, current amplification factor, emitter to collector current amplification factor. So the product of beta gamma is defined as the factor alpha, and it is called the current transfer ratio, which also represents the emitter to collector current amplification factor. So there is no real amplification between this current because alpha is smaller than unity. If we are saying it is amplification factor, but there is no real amplification because IC nearly equal to IE. So that ratio should be always less than unity. In practical case, IC is always less than IE. So this alpha is always smaller than unity, and the ideal condition alpha is equal to unity. So on the other hand, we can say that the relation between IC and IB, that is greater than unity, and that is promising for amplification. So that relation we can see next. So next is the base to collector current amplification factor. That means what is the ratio of IC to IB? That's we are going to see. So that represented as beta. So in accounting for the base current, we must include the rate at which electrons are lost from the base by injection across the emitter junction, that is IEN, and the rate of electron recombination with the holes in the base. So the base current means mainly due to this IEN as well as the base recombination current. So in each case, the lost electron must be resupplied through the base current IB. So if the fraction of this injected holes making it across the base without recombination is B, then it follows that 1 minus B is the fraction of recombining in the base. So we already said that B represents the number of holes that reached at the collector without recombination. So remaining, what is remaining? 1 minus B is remaining. That represents the holes that lost due to recombination. So that will be lost at the base side. So remaining is reached at the collector side. So this base current we can say that IB is equal to IN plus the recombination current. So the recombined factor is 1 minus B into IEP. So we can represent IB as IB consists of two contributors. One is IN and the another one is recombination current. So the recombination current is due to the recombination of holes with the electrons. So B amount of holes are reached at the collector. So the remaining 1 minus B amount of holes are recombined with the electrons. So that current is 1 minus B into IEP. That is the recombination current. So IB we can represent as IN plus 1 minus B into IEP. So we can see that this IC by IB ratio, then IC is we already defined as IC is BIEP. So the IC by IB ratio we can write as BIEP by IB now is IEN plus 1 minus B IEP, then divided throughout by IEN plus IEP. So you will get BIEP by IEN plus IEP divided by IEN by IEP plus IEN plus IEP plus 1 minus B IEP by IEN plus IEP. Then you can expand the bracket. So after simplification you will get it as IEP by IEN plus IEP is gamma. So you will get it as IC by IB is beta gamma divided by 1 minus beta gamma. In that beta gamma we already defined as alpha. So alpha by 1 minus alpha. We know that this IC by IB is called as current amplification factor beta. And the relation between beta and alpha is alpha by 1 minus alpha is equal to beta. We already proved that result. So this is called base to collector amplification factor. So the factor beta relating the collector current to the base current is the base to collector current amplification factor. Since alpha is near unity, it is clear that beta can be large for a good transistor and the collector current is large compared to the base current. So these are the different basic performance parameters of a transistor.